Good morning, everybody. Thank you for attending this Alter webinar session, which is a part of a student webinar series that we are hosting. Today, we start the track 2, where some advanced simulation topics are presented. Let me first introduce myself. My name is Hossein Shakourzadeh. I will be pleased to be the moderator for this session. You will have my background here. I got my PhD degree from University of Technology of Compiègne in 1993. Then I worked as a lecture researcher at UTC and professor assistant at Leonardo da Vinci Engineering School. Before joining Mechalog Software Company in 2000, in this company, Radios was developed, and Alter acquired Mechalog in 2006, and then I joined Alter France since this date, and I'm working on collaborations with universities and research centers. And also I'm in charge of collaborative research projects with both industry and university involved. So if it is the first time you attend to Alter student webinar series, please note that we are using GoToWebinar environment. As we have a large number of present participants, you will be muted throughout the whole session. However, you can use the question tab in this window to ask your questions. The demo recording and model files will be available after the webinar. The agenda for the session today is, as you see here. After my short introduction, a motivated and inspiring group of students from TU Vienna will present the structural analysis of their race car. Then my colleague César Barreto, senior IDEM engineer from Alter UK, will present the simulation of granular media with other IDEM software. The third presentation of the day will be handled by my colleague Pierre-Christophe Masson, who is expert group leader. He will present radios for crash analysis. And of course, we will have time for some questions and responses after each presentation. So before starting the technical presentations, I would like to mention what we call advanced simulation. In fact, it's not so easy to define what is advanced simulation, but at least we can say that if something is not a basic simulation using the traditional finite element method, then it may be an advanced topic. For example, here, when we simulate the explosion of a mine under a car, we have many topics to create, as high nonlinearities, time-dependent problem, large deformation of parts, and complex problem, contact problems, ruptures, and also the fact that we have to simulate structure and air for this simulation, so multiphysics problems. So all of these things make the problem, simulation problem, complex, and that's why it's an advanced simulation case. So in this first student webinar series, several advanced topics will be presented. Today we have the first session, And I invite you to register for next sessions in September, where other topics will be presented. One more thing before starting the technical presentation, I would like just to position radios and EDM solvers, which will be presented at this session. In fact, in the field of mechanics, computational methods allow to use massively computers to resolve complex problems. Several kinds of computational methods exist. Here, in this session, we will present finite elements method applied to crash analysis and discrete element method used in EDM. Here we compare radius and EDM solvers. Radius crash is used to study shock problems. It is suitable to simulate the behavior of assembled continuous parts by finite element method, where we want to compute the level of stress and strains and to understand if there is a rupture or not. And this is, for a crash, it's a transient dynamic problem because it's a very time-dependent problem, and the structure is deformed highly. One advantage of radius is the fact that we can couple it with other kinds of computational methods, other kinds of finite element analysis, CFT analysis for computational fluid dynamics, and multi-body systems. On the other hand, EDM is used to study granular medias. It is based on discrete element method, and it is used to simulate the behavior of individual particles. EDM has advanced contact models for complex granular shapes and can be coupled with several other computational methods as finite element method, CFT, and multi-body systems as well. Radius crash will be presented here by my colleague Pierre-Christophe Masson, who works in our global technical team as Advanced Structure Group Leader. And EDM will be presented by my colleague César Barreto, who is a Senior EDM Engineer. But before these two technical presentations, a group of students from TU Wien will present their interesting and very inspiring work on structural analysis of major Formula Student race car components. So Philippe Link will start with an introduction, then Rodolphe Rink present a drivetrain, and Philippe will take hand again and will present a wishbone, sorry, and the last part will be presented by Martin Molnar for sandwich structures. So let's start now.
Welcome to a presentation about structural analysis of major Formula Student race car components at TU Wien Racing. Today, we are going to present you 3 different simulations we've performed with Altair software to make our car faster. My name is Philipp Link. I'm part of TU Wien Racing since 2018, and I've worked there in the chassis and composite department doing implicit and explicit analysis. Right now, I'm focused on crash simulations using Altair's explicit solver Radius. And besides TU Wien Racing, I'm studying mechanical engineering at Vienna University of Technologies and have worked as a design engineer for a couple of years. TU Wien Racing is a 2006 founded Formula student team based in Vienna. Since the year 2013, we're building electric race cars, with which we're competing at Formula student events all over Europe. Our philosophy is to find the lightest possible solution, and that's the reason why nearly everything on our car is developed by ourselves. For example, our self-developed powertrain, so the electric motors, inverter, gearbox, and also the battery pack are all designed and analyzed by our engineers here in Vienna. To achieve the lightest, stiffest, or most efficient design in nearly every component, we perform a lot of analysis and optimizations during a racing season. For example, we use OptiStruct radios for structural analysis, or Inspire to create the next generation additive manufactured suspension component. To speed up our overall development process by reducing physical material testing time, we just started to use the multi-scale designer and do more and more material testing virtually, which is great. And regarding the electromagnetic simulations, we do those in flux to see how the magnetic fields in our self-developed motor spread. And last but not least, our vehicle dynamics department uses chassis sim to tell us what actually makes our car faster around the track. But for today's session, we will focus on structural analysis performed with OptiStruct. And for now, I will hand over the presentation to my colleague Rudolf, who will start with introducing you into a drivetrain simulation.
Hello and welcome to my presentation. In this session, we are going to talk about an analysis of a drivetrain assembly. We will use HyperWorks meshing tools for the mesh generation and optimization. We will talk about the contact analysis setup, and we will also take a look at nonlinear pretension analysis and using subload cases. My name is Rudolf. I'm studying mechanical engineering at the Vienna University of Technology. About my past in our team, from 2018 to 2019, I was a team member at TU Wien Racing. The following year, I was in charge of our team as the Chief Technology Officer. And from 2020 to today, I serve as the head of electric machines and as a member of suspension. My main responsibilities are the development of our motor, drivetrain, and wheel assembly. So what are we using this simulation for? First of all, we want to make an estimate on how the assembly deforms under load. So we want to make a stiffness evaluation. Secondly, we are always looking for opportunities for rate reduction. And last but not least, the displacement of our gearing components directly affects the gear meshing. So we want to calculate the exact displacement of our gears in order to later on compensate for that. Here's our quick overview of our CAD model. On the left, you can see the motor with our upright and the wheel hub attached to it. On the right, you can see a cross-section of our assembly, including the contact patch center point, which is here, at which we are going to apply the loads in the Y and the Z direction. Keep in mind that we are not going to simulate the tire and the rim itself, because that would increase simulation complexity a lot. And we are only going to use the rigid connection from the center point to the wheel hub itself. Taking a closer look at the wheel hub and drivetrain assembly, first of all, we are working with a planetary gear train design. So you can see the sun gear in the middle, the first and second stage of our planet, and our ring gear. In addition to that, we are using angular contact bearings. So in red, you can see the contact angle of both our bearings and the intersection with the center line. So at those points, we're going to constrain our model with rigids connected from here to the contact area of our bearings. In addition to that, we are going to apply tangential and radial forces at first and second stage of our gearing. Before we can start meshing our geometry, we first of all have to simplify our CAD model and remove any unnecessary geometries that are not necessary for the simulation and are not in critical areas. So we remove unnecessary bars, chamfers, or fillets that might interfere with meshing the geometry later. Regarding meshing itself, For the more complex shapes, we are using 3D tetramesh. And for other rotational symmetric parts, like the pin shafts, we're using hex elements. Reason for that is, for the more complex parts, it's often more time efficient to make a tetramesh. In addition to that, we are using 2D support meshes that you can see in blue, that we are using in local areas that we are either more interested in or we want to have more control over the mesh in certain areas. And of course, as usual, the usual rules for discretization and meshing apply. We also use the solid mesh optimization tool, in which you can define your required quality metrics of your mesh. You can check your elements for them, and if you have elements that do not meet those requirements, you can also use the fix function to make it automatically fix those elements if possible. Regarding contact definition, we first of all assume that we have a fully meshed geometry. And as we are dealing with 3D elements, we have to do a bit of a workaround for element selection. So first of all, we create a new 2D mesh using the function faces, which exactly matches our 3D mesh. The reason for that is that we can then select our elements that we want to select, first of all in the 2D mesh. Then we go over, we show the 3D mesh, and then we again select our elements by adjacent. This will then select the adjacent 3D elements from the selected 2D elements. And then we can create the contact group, select the respective element sets, and define a contact behavior. It is advantageous to stick to a human-readable naming convention when dealing with your contact sets. This will make things a bit easier, especially when dealing with larger models with many different sets. It is also a good idea to always check your contact sets accordingly, so you make sure that you selected the right elements that you want. Regarding the pretension definition, we again assume that we have a fully meshed geometry. And with using pretension, we can either use 1D or 3D bolt elements between selected nodes. In our case, we are using 1D C-rod elements between two rigid nodes. Under Analyze and Bolt Pretension, we can open the Pretension Manager, create a new load case, and select our bolt elements. So we select the bolt elements that we want to pretension. We create a new load collector that we call pretens1, and we also define the magnitude of our pretension, in this case 4,000 newtons per bolt. Following that, we create a new load step, which we call load step pretension, which is a nonlinear static load step in addition to the already existing external load step, in which the external load is applied to the tire. For that itself, we need to create some load step input cards called NL-parent, NL-adapt, and NL-out, which we first have to define. And then under the load step pretension, we can select those input cards, as well as the constraints that we defined earlier. And also under pretense, we select our pretense load case that we defined in the pretension manager. Lastly, when creating our external load step, we select our constraints and our loads as usual. In addition to that, under stat sub, we have to select our pretension load step. So when the solver solves our model, the pretension load step gets solved first, and the results from this load step will be then used as a starting point of our second load step. So this will take our pretension into account, and then we'll apply the loads externally. Thank you very much for your attention, and let me know if you have any questions.
Hello, and welcome back from my side. Now we're going to take a closer look at a simulation very relevant to our suspension department. I'm talking about linear buckling analysis of our fully laminated carbon fiber wishbones. During the development process of our wishbones, we do multiple implicit analysis with OptiStruct, and for this session right now, we're going to focus on the stability failure resulting in buckling of those hollow wishbones. And the key step here is the combination of a linear static and linear buckling load step which is needed to perform a linear buckling analysis. Right in the development process and during the finalization of the ply layer, we had some initial simulations running and performed physical testing with prototype wishbones. During those tests, we saw that buckling is an issue, and our critical failure modes were compression and buckling. And based on those results, we decided to further develop our simulation with a new focus on those critical failure modes to be able to develop a new ply layer, and we also adapted our choice of materials. To set up such a complex simulation, we do prefer to do very small steps, so start with a very simple model and add complexity with each step. So we started with an isotropic tube. In the next step, we changed the isotropic material into a MAT8 carbon fiber material, and just after that, focus on the wishbone itself. As mentioned before, in the linear buckling analysis, we need two load steps. First of all, we define a reference load, Pref, which is used in a linear static load step to calculate displacement, stresses, and strains, which are then used in a linear buckling load steps, which the linear buckling load steps is all about solving an eigenvalue problem, which gets you the critical loads and the certain buckling modes happening there. To provide the input data for the linear buckling load step, we need to define an IGRL card, which is basically about what eigenvalues you want to calculate. And now let me just jump into my HyperWorks. Here we can see the carbon fiber tube. So the meshing, the properties, the materials is already done. We just have to look at our load steps. Here is our tube. We see our constraints, our loads. They are here. Yeah, the SPC, the force, all right. And also down there. That's good. Great. So have a look at the load step. We already have one defined here. That's our linear static load step. So for the linear buckling load step, we need to define our card first. So that's done by using the load step input. It's already popping up. So we're defining our eigenvalues, range of interest here. Should be fine, frequencies. Buckling. That's done. And now we can define our load step. Which is about linear buckling. We need to choose the right analyze type. Linear buckling, alright. For the stat sub, we have our initial, our linear static load step, of course, and the method is here, our already defined card. And now the model should be ready to calculate. That's all it takes. And I'm switching back into my presentation. Looking at our final model, we tried to model the physical testing as precisely as possible. Regarding the wishbone itself, such a great level of detail meant to model the carbon fiber structure of the wishbone, the inserts, and even the ball joint very precisely. In the composite menu, you can see all the different materials we have used for the simulation, and I've been talking about the physical testing. That testing was used to, on the one hand, validate our simulation, and on the other hand, to calibrate our strain gauges, which are mounted on the wishbone, on our final wishbones. Overall, for the modeling, we used a second order combination of quads and trias. For the laminate, we used the ply-based modeling approach, so P-comp-P property with a MAT8 material card. And for inserts test devices, we used a three-dimensional mesh with a MAT1 material, and the stacked areas of the wishbone, so the fully solid carbon fiber areas around the uniball where the ball joint sits. Also uses a three-dimensional mesh with a Mat9 orthotropic material card. The ball joint is modeled with a 1D joint element, in this case the FV ball, which is connected with a combination of RB2 and RB3 elements to our outer ball joint housing and the bolt of our test device. And as mentioned before, the stacked carbon fibers, so fully solid carbon fiber area, the purple ring you can see in the picture below, is modeled with a three-dimensional mesh and is connected via a contact to the rest of the laminate. Looking at our results of the linear static load case, in this case the composite failure index, which is for the whole structure below 1, which is good and tells us that our laminate is not likely to fail. We use the Tsai-Wu failure theory, which can be chosen in the P-COM-P property card. And looking at the linear buckling analysis, you get your different buckling modes at your different loads, and you need to investigate what buckling modes and, in further case, what critical loads are you need to consider in your application. Because if you look at our wishbone here, we have two arms of the wishbone. One arm is fixed into the test machine, so both ends are constrained. But the other arm, one arm is not constrained, so this end is allowed to move, and we should not consider that in our buckling analysis. So we need to find the buckling modes relevant to our application and define the critical loads after that. In the end, we were able to predict the global buckling failure of our prototype wishbones quite precisely. And with that simulation, we were able to define our new ply layup and also took a look at the local buckling modes and took those into consideration at developing the new layup. With our final wishbones, we were able to achieve a difference in stiffness regarding simulation and physical testing of less than 10%. So at that point, the simulation fulfilled all initial goals, and the wishbone was further evaluated in an assembly simulation. So that's it from the wishbone development. I have to thank you for your attention, and I hand over the presentation to my colleague Martin.
Hi and welcome to the last part of our presentation. My name is Martin Molnar. I study mechanical engineering at Vienna University of Technology. I joined TU Wien Racing back in 2018 as member of Composites. Then I became head of chassis, and since 2019 I'm member of chassis and composites development. I'm currently working on the suspension pickup points. And today I will be talking about sandwich structure and specifically about 3-point bending. And from a student, we have some rules regarding structural integrity, equivalency, which leads to driver safety. So we need to split up the monocoque in different parts and make some physical tests to pass this document. And for this reason, we use HyperWorks OptiStruct to simulate the panels before we could test them. But first, we start with a calculation to get an idea about the material behavior and the stiffness of the structure itself. Then we make some basic simulations, and to get the right ply layup, then we do physical testing, and if the test panels pass this document, then they build the base layup of the monocoque. But we also use the data from physical testing to refine the boundary condition, and also for more complex simulations where we model the sandwich structure itself and also the suspension pickup points, the inserts, and the splice adhesive. With this data, we then can improve on performance globally and locally. But today I will be concentrating on ply-based basic simulation, and at the end I will compare the results from this simulation to physical testing and also to calculation and modeling the sandwich structure as well. So first of all, I will show you how to set up a basic ply-based simulation for 3-point bending, where the sandwich structure is modeled as a ply. So the panel which is to be simulated is 275 by 500 millimeters, and the force acting on it is around 8 kilonewtons. Here you can see the material data used for this simulation. If you want to make the simulation yourself, then use the data in this picture. Then a short tutorial about the basic simulation. So first of all, we need to create a surface that we can mesh afterwards. It's 500 by 275 millimeters. Then we create the mesh on the surface. For the beginning I did a 5 millimeter mesh. Then you need to check for the element normals, if they are all showing in the same direction, and also the material orientation, which is very important, that all the elements look in the same direction. If it's not the case, then you can adjust it by a vector, which you then project to the elements, so that all the elements look in the same direction. Then you can define the materials given in the presentation for this simulation. We are gonna use 3 different materials, one unidirectional, one cloth, and one core. The core is an aluminium honeycomb with 40 millimeter height, and after we finish defining the materials, we can start with the composite itself. But before that, let us make the test rig, the coordinates, the nodes for the test rig, and then we can start with the plies. As you can see, I define 3 plies, one in 45 degrees, one in 0, the unidirectional, and one in minus 45 degrees. Then I define the core, but we are going to use the symmetry of this layup, so the core is half as thick as it needs to be, so that after applying a symmetry to the laminate itself, it has the right thickness. Now laminate you can make under composites and then drag and drop the plies to the right laminate. And then you also need to add the property, a composites property for this. I use the P card, and here you can check for the right thickness. It's a representation of the panel, and after you check if everything's correct, just add another component, rigid, where we define the test rig itself. It's very useful to have RB2 elements for this setup, because you can adjust the degree of freedoms of every node vertically. Then you can also add your load collectors for the single point constraints, and also for the load. The load, as I already mentioned, is around 8 kilonewtons, and this node must only move into one direction, downwards, minus Z direction. Then you can also refine the degree of freedoms of the rigids, and also the SPCs down there. So after everything is defined, you can define your load step, the load step, and start your simulation. For the simulation, for the results, I used a different model. The model I use for the results is more refined and has a finer mesh. And as you can see, the result is around 12mm displacement. And in HyperWorks 2021, you can also look at the displacement and stresses directly in HyperWorks itself, so you don't need to open HyperView. You don't necessarily need to open HyperView, and it's very good. And it's also very good to look at the deformed state of the simulation as well, so that you can check for any error in the boundary conditions as well. But why are we doing a simulation like that if we could also just use ESAComp and do the calculation or the simulation in there? We use it to set the boundary conditions right and to get an idea about the structure itself. And with the knowledge we gather from this basic simulation, we head over to a more specific simulation where the core is modeled as well. And here, as you can see, we start with basic boundary conditions, and then we get over to more detailed simulation where the testing rig is modeled as well. And with this data, we can then model and simulate the suspension pickup points as well. But not at least, a comparison of different methods, and the calculation and ply-based simulations are a bit more stiff than the physical test, but you can see a good correlation in between the ply-based simulation and physical test already, and we could further improve the correlation between the modeled core and physical testing. Keep in mind that the testing rig has also a stiffness, so that the results from the tests aren't necessarily the results that we are looking for. We need to subtract the stiffness of the testing rig from the results as well. And at this point, I want to thank Altair in name of TU Wien Racing for the support and for their products, and we are happy to answer your questions.
So thank you, Philippe, Rodolphe, and Martin, for this interesting and very high-level presentation. Unfortunately, we had some troubles with the sound and a little bit noisy, so we hope that we can reduce the noises during recordings. So hopefully we will have this recording with better quality of sound. Now we have a short time for some questions. I think we had several questions answered by my colleague Jan, actually, but some other questions maybe come to about the presentation. Do you have some questions to ask to Philippe, or Rodolphe, or Martin? From my side, I have one question for you. I think these kinds of projects are very interesting for learning. So just how, Philippe, Rodolphe, and Martin, how we can motivate all other students here about what you can learn by applying what you learn in the theoretical courses, just by application to the race car, what you can learn and what did you learn and how it can contribute to your education.
Yeah. I think it's the best way of learning things is like doing them, and with such a project in the former student area, it's really for a lot of people, it's the first time they're building something, they're doing something, and they need to finish a project in time, which is absolutely great in learning all the different techniques and all the technical stuff and organization stuff. So if I can just speak for myself, but the project itself helped me a lot to improve my engineering and improve my skills in a great variety of ways and levels.
Okay, thank you. And we have another question about how long does it take to use HyperWorks at this level? I mean, of course, it's because, in fact, it's advanced level. So did you receive training session? Did you use some recorded session, you know, e-learning materials available on Alter website? And what was the ramp-up way you could access to all these high-level techniques? Philippe, Rodolfo, Martin, who can answer?
Yeah, so if I can speak again just for myself, but it's a process. So you first of all, we did have some training from some other team members and also from Altea. So we do have some trainings regarding the basics of the software, and from that you just start with an easy problem and work yourself up from there. So you mainly start with just basic static problems, meshing them, and yeah, I think it did take us maybe half a year to get to a usable level that we can work with on our race car for the parts, but that might vary from person to person. So it might depend on how much time you actually spend on using the program, and yeah, so you could say it will take a couple of months to get into it.
Yeah, thank you very much. We have several other questions are coming, but we have to start the other session as well, presentation as well. Just to maybe to finish with another question is about the simulation and physical testing. In fact, we know that simulation reduces a lot the time of study. I mean, to do iterations, to understand better, to come back and redesign parts. But in your case, is even if the testing is very expensive and takes a lot of time, do you think that you will have some possibilities to go to testing, or even if for simple tests, for instance, for the composite part, for the bending test, or something like this? Philippe, Rodolphe, Martin?
So the question is about testing, how we can make sure that we don't spend too much money on testing, or just to be clear.
Okay.
No, I mean, I wanted to ask to understand the question fully. So how was it meant? Because we need to test, for example, the 3-point bending. We need to test it for the regulations, so we can use the data to improve our models. But the wishbones, it's a critical part. So if they fail, then we might crash the car. So we most of the time check the wishbones as well, so that they so the wishbones surely withstand the forces acting on them. So it might be expensive, but if we crash the car, it's more expensive. So yeah, And you also need to keep in mind that simulation isn't always showing the correct results. It depends on the person doing the simulation and also on the boundary conditions. So just to be sure, we try to evaluate the simulations so that we didn't make any major mistakes.
No, thank you very much again. That's a very nice presentation and great job done. Not easy. So I hope this work can inspire other to go to the project, because by doing project we learn a lot. And so thank you again all for presentation. And let's go to the next one. So the second presentation is about particle simulation with Alter Idem. So the speaker is Cesar Barreto, who works at Alter UK as senior IDEM engineer. We have his profile here. So bachelor degree in mechanical engineering and MSc in energy resources from Heriot-Watt University. He's now part of IDEM engineering team in Edinburgh, and he provides technical support to new and existing IDEM users. Cesar is focused on producing e-learning materials, and he helps our customers to learn more about IDEM. So let's start with Cesar presentation.
Hello and welcome everyone. Thanks for joining our IDEM section today. My name is Cesar Barreto and I will be your presenter. I provide technical support to new and existing IDEM users, and I focus on producing e-learning material that will introduce you to current and new IDEM tools and will help you to speed up with the software. As we all know, many industries and applications involve ball and granular materials that are interacting with machines. And the use of Alter Idem software can really help you when trying to understand and optimize ball material handling equipment. This is the agenda for today. I will start with a definition of DEM, as it may be a new term for many of you. Then, I will give you an introduction to the Alter Idem software and the basics of how it works. We will do a short demo to demonstrate the IDEM interface and also the different components. And finally, I will show you an example when IDEM is coupled with Motion Solve. So let's start. DEM is a way of simulating discrete matter, in our case particles, that represent granular material, or any particle that we want to simulate. So in IDEM, the particles are assumed to be rigid, but small overlaps are allowed to represent deformations during contact. And because of the existence of those overlaps, we can calculate normal and tangential forces between the particles. Here is a simple example of three particles colliding. At the beginning, the particles are assigned with initial linear and rotational velocities. There is no forces acting on those particles. But then they move closer to each other and finally they collide, as we can see there. When they collide, overlaps are created and then we can have normal and tangential forces acting on those particles. Then the algorithm calculates the resultant forces and moments acting on each particle. Finally, numerical integration is used to update the linear and rotational velocities, positions, and orientations. So it can be seen in the animation how both linear and rotational velocities change during the collision. So DEM works when particles are in contact, and by applying a contact model that describes the physics of how particles will behave when they are in contact with each other or equipment, then Eden is capable of calculating forces acting on those particles. And after updating positions, then the software looks for new contact with other particles or geometries. We get the updates, and finally the whole process starts again. So this slide summarizes the basic principle of particle behavior when using Eden. Granular material can be very complex, and a lot of engineers try to make sense how that affects their equipment and processes. So Eden can be used in a wide range of industries, anywhere where ball materials are present. This includes the heavy equipment industry, looking at virtual testing of dump trucks, bodies. Here we have a truck excavator, also harvesters, and many others. It is also used in the mining and metal industry to test and verify performance of conveyor belts, transfer points, crushers, grinding mills, and also in the agriculture industry as well, as we can see here. That is Eden coupled with Motion Solve, and I will explain an example later on during the presentation. We can also evaluate and optimize the design and performance of cars on different terrains. And we can model the interaction between the body parts and the soil. We can also simulate mixing processes, for example powders, and analyze the mixing effectiveness by showing the concentration of each type of particles in the mixer. Another industry is process manufacturing, where Eden can be used to optimize process involving bulk solids such as powder mixing, tablet coating, milling, drying, and many others. You can really simulate so many different types of materials, including flexible materials. Now that we looked at some examples, let's move on, and I'll explain how Eden software works. When we set up a simulation, we want to be that simulation as close as possible to reality. And to achieve that, you have to define material properties, like the one shown on the left image. You have to define density, shear modulus, Poisson ratio. Then you have to define particle shape and also the size distribution that will give you a representation of the real material. And you will need all those inputs to start your simulation. Once you have all the input data, the next step is the calibration stage. And this is a real physical test that will ensure that your simulation shows real material behavior and also give you confidence that the simulation is representative to a real case. And that is what you want to achieve, a case scenario that is very close to your real application. And finally, on the right, we have the contact models. That are the physics laws and equations that describe the behavior of those particles when they're interacting between each other, and also, as I mentioned, the particles with the equipment as well. Here we can see the main 4 base models, and they are used for different kinds of materials. They are all based on quantum mechanics theories. For instance, the JKR introduced attractive forces to the particle. We also have the Hertz-Millen, that is the default model in Eden, the Edinburgh model that is used for stress-dependent material, and his theoretic spring model. I won't go into details about quantum models, as this is not the aim of this presentation. However, here we can see a schematic of the different Eden quantum models. So you can choose one of the base models, then a rolling friction model and additional models. You can chain them together to best represent your application. And all these components combined together produce a fit-for-purpose ball material flow behavior, and that is what we want to achieve. Now let's move to the next section. For the Eden demo, we're going to do the mixing tutorial. And in this demo, I'm going to present the 3 different components of Eden, starting with the Eden creator, where we set up the model, then the Eden simulator, where we run the model, and finally the analysis, that is the post-processing section of IDEM. Let's start with the IDEM creator. Here we have the creator interface, and the first thing we have to do is to set the measurement units. Once we do that, then we move to the creator tree, and we work our way from top to bottom. First, define the granular material. Right-click and select Add Ball Material. Then you have to define the material properties. That includes the Poisson ratio, solid density, and the properties we spoke at the beginning of the presentation. Then you have to define material interactions, and that includes the coefficient of static friction, coefficient of rolling friction. All these material properties are very important, and you should get that information from literature or previous projects. However, if you don't have that information at all, I will show you after the end of this first part of the creator which tools you have available in IDEM to help you to start with this. After that, it's a good practice to rename the ball material, and in this case will help us to identify the different particles that we're using in our simulation. Next, we have to create the particles. Remember that the particle shape in your simulation, it will depend on the kind of analysis you would like to do, and also the dimension of your particles. For this demo, we are going to create a 3-sphere particle. So we just add a particle and then create and position each of those spheres. The radius of each sphere is 3 millimeters, which is quite a large particle. Also on the left-hand side, you have the shape library that will help you to start with any of those default particle shapes. And also on the right, you have the particle generation tool that will allow you to import a CAD template, and then IDEM will generate those particles based on that template. Next, we have to set the particle size distribution, and this will provide you some real behavior to the material. However, keep in mind that if you have a large size distribution with tiny particles and large particles, that will impact your simulation time. For this example, we are using a fixed size distribution. Also, anytime that you do any modification to your particle, remember to press Calculate Properties. Next, we're going to rename the particle and call it base. After this, we're going to duplicate the particle, because we have 3 different types of particles: base, middle, and top. Right-click on your ball material and create 2 copies. After that, you have to rename the ball material and the particles. And this is what you should get. Next, we have to define the equipment material. And in the same way, we just right-click on the equipment material and then we rename it steel. In a similar way, we're going to define the steel properties and also the interactions with the 3 different tablets. Once all the ball and equipment material are set, the next step is to move to the geometries section. And in here is where we import all the CAD geometries that we're going to use, and also to add any motions and kinematics. Then right-click on geometries and import the CAD geometry. Once you select the CAD geometry, you have to specify the units. Click OK. And for our demo, we are going to merge all the blades parts in one. So right-click, press Merge Geometry, and select them all. Now, we're going to rename it as blades. And also, we're going to rename the other geometry as a drum. In IDEM, you can define different kinds of kinematics. You can define translation, rotations, and also sinusoidal kinematics. We also have force and torque controllers, where you can input a time-dependent equation to specify the force or torque on your equipment. For our case, we have to set the initial velocity and also to set the axis of rotation. The display vector is very useful, so you will know if the axis of rotation that you have assigned is correct. After this, we are going to copy the rotation motions to the blades, as they have the same kinematics as the drum. Now we have to create a factory. And remember, a factory is the term we use in IDEM to introduce material or particles into the simulation space. So right-click on the geometry that you will use as a factory, in this case it's a drum, and a factory, and we're going to rename it. In IDEM, we have two different types of factories, static factories and dynamic factories. In this demo, we're going to use a static factory, and the difference is that static will create all the material in one time step. Then you have to set the particle generation properties and select the material. Remember, we are creating three different types of material that are the three different tablets. After this point, we're going to copy the factory base twice to create factory middle and factory top, and we're going to rename it. I won't show you the details of how to create the other two factories, as it's exactly the same what we did with factory base. And here we have the three factories created. Next is the physics sections. And this is the section where we define the contact models we want to use. For this example, we're going to use the Hertz-Midland contact model, that is the default model in IDEM, for both particle-to-particle and particle-to-geometry. And finally, we have the environment section, that is the final section of the creator tree. These are all the different parts of the creator tree. And now we can save the model. Okay, so now that we finished setting up our simulation in the IDEM Creator, I'm going to give you some guidance on how you can optimize your simulation. We're going to cover three sections: factories, creating materials, that will be your ball material, and then geometries. Let's start with factories. A factory is a term we use in IDEM to introduce material into the simulation space. So in this part of the presentation, I want to give you some tips how you can improve or optimize your factory. The key point here is that no particle will be created that touches another particle or a geometry. And because of this, it is important to make sure that your factory geometry have the correct size for the creation rate that you're using, the one that you set. Otherwise, you will find the IDEM struggles to find a space for particle creation, as you can see in this video. And if you think your simulation is running slowly because of factory settings, you can resolve this. Move to the IDEM Creator and then increase the size of your factory geometry. Also, you can lower the creation rate. And finally, you can assign an initial velocity to the material. Another point that you should keep in mind is check your solve report. In here, you can see if you have a high number of particles regenerated. That's an indication that your simulation is running slowly because of the factory. So what we're going to do is adjust the factory settings and see what happened with the solve report. We're going to reduce the generation rate, save the simulation, and then run the simulation again. We clearly see that the material is flowing so much better. If we stop and then check the factory, now we can check the particle properties, and there is some regeneration. However, there are no particles that fail, and that's an indication that our factory is running as expected. Let's go into the second section, that is creating materials. And at this point, if you remember in the demo, we have all the properties of the material like density, Poisson ratio, and so on. If by any chance you don't have that information, then it then comes with a series of material model libraries that you can use as a starting point for the simulation. So first we have the GEM database that is based on the angle of repose and the inclined plane test. In here, you only need to answer 3 questions about your material to obtain a material model. The questions are, which is the size of your application? So you just select roughly which is the size, then what is the pole density of your material? And finally, what is the angle of repose? That is a test that you will do. Here you have a table where you need some engineering judgment to choose the correct material. All depends if you have a free-flowing material or a sticky material. Once you select your material, then you will be presented with a table. And in this table, we can see the final material properties and also coefficients that you will use in your simulation as a starting point. Once you click Finish, you can see that the pole and equipment materials have been assigned in your Eden creator. Also the particles as well. And the final material model library is the powder starter pack. So powders are used in different applications in the pharmaceutical industry, also additive manufacturing, and chemicals and other process manufacturing industries as well. This powder starter pack is designed to be useful for anyone that would like to start your simulation, obviously using powders. And it has a selection of 9 material models, and they represent a range of materials with different flow properties and also compressibilities. And all these models use the Edinburgh elastoplastic addition model, have been designed to simulate these complex cohesive materials. And we can see the table on the right. In this video, you can visualize the difference in mixing free-flowing powder and cohesive pure-flowing powder. In the same way, you have different folders with all the 9 material models to choose from. And finally, to finish with the creator component, we have the geometries section. In here we have the parent-child feature. So this is used to link the motion of geometries together, so that complex simulations can be defined in a fast and a simple way. And you just have to define which is the parent and which is the child. And we can see here, so the first object, we define the kinematic, and then that kinematic is kept, and we just transfer that to the second and third object. And we can see in this example of a mixer. Also, you are able to replace geometries, and this is useful in the case you want to investigate different designs. And finally, I would like to point out that you have this multiple copy option where you have to define only once the kinematics, and then that kinematic can be transferred or can be copied to the other ones, and with a delay time. And we'll see here how it works. So we can see at the moment, only for one object, the kinematic has been defined. But then we can create multiple copies. And those kinematics that we define for object number 1 can be copied to any number that we can define here. We just need to tell the software what is the delay time. So when we save the simulation and then play, we can see what's happening. We can create the object 1, 2, 3, all following the same kinematics as the first object that we set. And that's it. That's what I wanted to mention regarding the creator. So let's go back to the Eden demo. And the next component is the Eden simulator. This is the interface for the simulator. And here is where we run the simulation. On the left-hand side, we have to set different parameters, and that includes the time step, that it should be small enough to guarantee stability in the simulation. And that will depend also on the contact model and material parameters. We also set the total simulation time and the simulator grid. You will have the option between CPU and GPU engine, and you can also choose between OpenCL or CUDA solver. And once you have all this set, then you can press play. So as we all know, DM is a very computationally intensive method, and speed is always a key aspect for simulations. So in the next section, I'm going to give you some guidance on how you can speed up your simulation and some of the parameters that you can check to see if you can change it and then run a simulation quicker. Once we reach the total simulation time, we are ready to analyze the results and move to the Eden analyst. But before that, let's see some guidance regarding the Eden simulator. I'm going to mention the key parameters that you can modify to speed up your simulation. And the first parameter that I'm going to mention is the shear modulus. So this shear modulus value has a significant effect on simulation time step. And remember, the time step is very small in Eden. Otherwise, we could experience a strange particle behavior, like exploding, for example. And typically, the shear modulus value can be decreased to speed up the simulation without any effect on your results. And this is something that we usually mention because users want to use the real shear modulus of the material, when in reality, they can speed up the simulation by decreasing this value. The second parameter that has a significant influence on the computational time is the number of particles that we use to represent a particle shape. And that makes sense because then we will have more contacts, so more calculations. So the rule here is simple particle shapes are often enough to capture the bond behavior. However, when you have those cases where the particle morphology is well defined, for example, tablets, then you can use the particle generation tool in Eden to help you to create those shapes. Also, particle size distribution is another way of keeping realistic material behavior. But sometimes, when we have finds in the simulation, we could remove those small particles. Often finds don't have a significant effect on the ball material response, and the reason is because the mass fraction of the fine particle is very low, especially if we are talking about coarse materials. And if you can remove the fines, then you can reduce computational time. Also, you can upscale the particle mean size and maintain the particle size distribution in your model. And by doing this, you can still capture the particle size segregation effect. In here, you can turn compressed data on or off. So if it's off, it will save some CPU power. However, your file will be larger. Also, you can reduce the save data frequency. And as well, you can select which data you would like to save. That will also speed up your simulation. And finally, for large simulations with thousands or millions of particles, we also recommend using a GPU engine. And that's pretty much all the guidance for this part of the presentation. I will explain the last component of the software, that is the Eden analyst. We're going to go back to the Eden demo. And before I start, remember we started with the creator, where we set up the model. Then we switch to the simulator, where we run the simulation. And now the Eden analyst, that is the post-processing section of Eden. First, we're going to assign different colors to each of the particles. Starting with the base particle, And in the same way, we can color the middle and the top particle. After doing this, we are gonna play the simulation and see what is happening in the mixer. And we can actually see what's happening after 2 rotations in the mixer. Next, I will use selections. Selections allow to monitor particles passing through a volume known as a bin. For example, you can use them to determine the mass flow analysis within a specific region. In our example, we're using bin groups to determine how many particles are in that specific area. Here there is different options where we can set the bins. Including the dimensions and also the display option. We can all have the options if we want to always see it or only when it's populated. Next, we will create 3 queries, one for each particle type. And that will allow us to determine how many particles are in each bin. Then I do some subsection coloring to see the particles distribution throughout the simulation. The different colors give an indication where the particles are accumulating, and this is done for each time step. And also you're able to display the numbers of particles in each bin. To do that, you have to turn on the option. And here we can see the exact number of particles we have selected. And in this image, give you a representation of the kind of analysis that you can do and to understand the mixing efficiency of the equipment. We can also create plots within them to analyze our results. And in here, we're going to determine the contact forces between layers. You have to select the right attributes and also the settings to generate your plot. Once the graph is created, it will give you a better insight of how the equipment is working and also on how the base and top particles are getting mixed. As we can see in the plot, there are no contacts at the beginning of the simulation. However, as time passes and the drum spins, there are more and more contact between the base and top particles. In the same way, you can do it for the other type of particles. And we can see the number of contacts between the base and middle tablets. Also, if you would like to plot in any other post-processing tool, you're able to export this data. In this final part of the hidden analysis, I would like to highlight some more examples when using selections. Also, talk about sensors. And finally, I would like to highlight some of the tools that are available to create dynamic videos in them. So let's start with the examples. Here we have a mixer, and all those 3 bands that you see there, those 3 different colors, they were created using selections. And they are used to analyze the mixing efficiency of the equipment, in this case, a mixer. In here, geometric bins were set up to track the material passing through the sections of interest, and we have created 2 boxes, one blue color one or purple one, and kind of a pen one. And finally, we have this graph bucket, where we can use selections to understand the handling of different materials. And as well, we can track the amount of material moved with different operational settings for the graph bucket from one box to the other one. We can also investigate which is the ideal speed of the bucket to avoid spillage. Also, you have sensors in the Eden analysis, and they will allow you to measure mass flow rate, total mass, density, and velocity of your ball material. When you use sensors, you are able to see the numerical value on the screen, but also you are able to export that data or do the plots in Eden. And the way we do the setup is very similar to selections. So you just right-click and select any of the sensors available. Then we have to do the settings. So what I mean is you have to select if you want to see the sensor always or only when it's populated, also the geometry, and then the location and the dimensions of that sensor. One other thing, the sensor's position can be linked to a geometry, and this is useful when analyzing moving material with geometries. So this bucket elevator tutorial shows different sensors, which help to analyze the process via visualization, or you can use some plotting as well. For this tutorial, we will plot mass flow rate for sensor 1. And here, and we can see. And finally, we can see a vibration screening process, where total mass sensors were added to measure the total pass mass at each different deck. So we can see number 1, 2, and 3. And finally, let's check the last point, that is how you can create videos in Eden. Eden has the ability to track a geometry, and this is very helpful when your simulation includes many moving parts and you are interested in one specific object, for example here, the green bucket. First, you must create a new camera view and save that view to a system view, as you can see at the top there. Then edit the view and tick the track geometry box. Set the camera view and positions, and once you're ready, click Apply. And finally, we have the playback scheduler. In here, you can change the view when creating your video. And this is useful if you want to compare different designs. So you have to create and name each of the views that you would like to have. After that, you are able to import or export any view already created. And this tool is useful for comparison when you are running different simulations and want to compare different designs or different material floors. Then you have to tell Eden when you want to apply the view that you already saved. And in this example, we can see how first we want diameter, then it changed into velocity, and finally we change the view. And this takes me to the end of the Eden demo, where we cover the 3 components: the Eden Creator, the Eden Simulator, and the Eden Analyst. Now, let's move to the last part of this presentation, that is the Eden and Motion Solve example. Eden can be coupled with other alter tools, including ArcuSolve, SimSolid, and Motion Solve. Today, we're going to see an example between Eden and Motion Solve. The Eden Motion Solve coupling transfers the ball material load directly from Eden into Motion Solve. Then the ball material loads are used in Motion Solve to understand the effect on the equipment dynamics. The objective dynamics are passed back to Eden to provide a realistic force feedback throughout the simulation. Here we have an excavator model that is already set up in MotionSolve, all the geometry, graphics, forces, and motions. And the model is ready to be run. In the same way, we have already set up the model in Eden. We have defined the ball material properties and also the physics that are the contact models. Also, we have created a factory. In this case, the factory is moving, and in this way, we are providing more space for the particle to be created. Then we move to the simulator and we run the simulation. Once all the ball material is created, we can save the simulation. We can go to the analysis and then export the simulation at the last time step. And then we set the time to 0. In this way, we are creating an Eden simulation where the ball material has already been generated. Also, we can remove the factory geometry because we don't need it during the Eden and MotionSolve coupling. Then we can adjust the domain. Once your simulation is all set, you can start the coupling server. In MotionSolve, you can create the Eden subsystem, and here you have all the tools to couple with Eden. The aim of this short video is to show you the type of analysis you can do when Eden is coupled with MotionSolve. However, for any of you that is interested in the full details of how to couple Eden with MotionSolve, there is a dedicated course in the Alter Eden e-learning, and it's available in the website. Once the requested code simulation time is complete, then you can analyze the results in Eden and also in Hyperview. You can estimate stress and loads from the ball material interaction with the excavator. In this example, we can see the stress on the equipment part when handling two different ball materials, called an iron ore. And this is the end of the presentation. But before we start with the Q&A section, I would like to point out that we have an Eden e-learning section on the website where you can find much more details and further information about the tools and the Eden components that we covered today. And thank you very much for your time today.
Thank you, Cesar, for this interesting presentation. From my side, personally, I learned a lot. I hope this presentation was useful for all attendees. So we go through the question answer session now. We have a small time for some questions. Just some questions have already been asked, so and response in the question tab. If you have other questions, please use the question tab to ask more questions. From my side, I take advantage of this time just to mention you that Eden is a part of Alter student version, which is available for free for all students. So you can take advantage of your student period and go to our website alteruniversity.com and get the free version for 1 year. We have e-learning materials available on this website, and you can use Eden, learn about that, and use it for free. we have some questions coming up for you, Cesar. So one question is, can we capture temperature in EDEM?
Yes, so the answer is we have different contact models in EDEM, and one of them is temperature. So you can transfer the temperature between the geometry to the particle, or the other way around, between the particle to the geometry and between particles. Of course, all depends, temperature is quite complex, and all depends on the kind of simulation you would like to do.
Great. Another question is about friction model, and if the friction model is considered in EDEM. I think yes, but
and yes, it is considered as well, and we have two friction models. There is, in fact, one that is implemented in the next release, and again, will depend on the kind of simulation. Remember, where you are setting the morphology, the shape of your particle. If you're using different spheres, then you're already introducing that resistance to rolling, to friction. But to answer your question, yes, we have friction models in them.
Thank you. So one question from my side. Is there a limitation with the number of particles that we simulate in EDEM?
So this is a very actually interesting question, and also it's very common as well. So many people, when they start using the software, they want to know which are my limitations, and the answer is there is no limit on the number of particles. However, you need to find a balance about how long you want to run your simulation and the accuracy of the results. As time, you have limit on time, so you can run your simulation, depends on the project. Then you need to guarantee that you're not running millions, but you are only focused in the area of interest. And one thing that I would like to highlight here is that, remember, if you're using small particles, then you will require small time steps, and that means long simulation times. So the question is, there is no limit. Sorry, the answer, but keep in mind the size of your particle.
Okay, thank you. So if, for instance, we use a laptop, a computer, personal computer. So we can do some projects with student can do some projects using EDEM, of course, with even if with their personal computer, I assume. Yeah. Okay, thank you. And another question about the shape of particles. So we have, if I understand well, we have multisphere and polyhedral particles in EDEM, and when should I use them?
So all depends. During the presentation, we mainly see multisphere particles. However, we also have polyhedral particles, and all depends on the type of application you want to address. For example, when you're using very specific shape particles that they have high aspect ratio, for example, I'm talking about tablets or cubes, something very, very specific, then you will use, I will recommend use polyhedral, but it will be faster. However, for most applications, the well-validated multi-sphere approach, I think that will provide you with a fast and accurate calculation of contact forces that are the physics.
Okay, and so you need some experimental results to calibrate, different kinds of media.
Yeah, and we spoke during the presentation very quick about the different material libraries that we have. That's a starting point for the calibration. And calibration is a key point in EDEM, because then you are guaranteed that your simulation is representing something that is real. And what you have to do is just a methodology where you're trying to match what you set in EDEM with the real material property, for example, ball density. And then after you match that ball density, then you match with the test, a real test. For example, angle of repose. This is very simple. It's just a cylinder. You just lift it, and then you measure the angle. That angle that you measure for real, then you just measure that, not measure, but try to match by changing the ball material property within the software. And once that is matched, then you go to the next step, and that's the calibration. It's just a methodology to prove that the simulation is telling you is representative to the real application.
Okay, thank you very much, Cesar, for your presentation. I think we have to jump to the next presentation. I would like just to mention that for students interested to learn more about them, theoretical aspect, we have also an ebook available, and they can learn more about the theory and what is behind the solver. Thank you again. So
thank you.
Let's go to the third presentation. So it is about crash analysis with radios. The speaker is Pierre-Christophe Masson from Alter France. He's working in Alter Global team as advanced structure group leader. His profile is here. So he got his engineering degree from École Centrale Marseille in 1999. And then at the same year, a master degree in applied mechanics from Aix-Marseille University. Since 2002, 2007, he worked as a project engineer and project manager at Mechalog Eurosim company before joining Alter in 2008, and he was a senior application engineer and technical specialist up to 2020, and from this year he's a group leader at Alter Global technical team. Sorry. So let us start with this presentation.
Hello, and welcome to this introduction to crash analysis. In this seminar, we are first going to see what is crash and why people are doing crash analysis. Then, I'm going to speak about explicit methods and why they are well adapted to crash simulation. Next, I'm going to introduce what is Alter Radios and what does it solve. After, I'm going to detail the standard workflow to set up and run this type of simulations. And finally, we are going to see the application of this to the simulation of a honeycomb crash box. So let's start with what crash analysis usually cover and why people are doing crash analysis. Crash analysis are basically impact at speed higher than 1 meter per second and usually lower than 100 meters per second. In standard vehicles development, they often also cover all cases leading to high deformations, and generally all analyses related to passive safety. Now let's see why doing crash analysis. We are doing crash analysis to assure and improve the safety of vehicles occupants, to ensure the safety of pedestrians too, and also to ensure structure and system safety, such as a wing hit by a bird batteries impacted by other vehicles, and so on. All these concerns are the subject of regulations first. Regulations for automotive, aviation or rail. All the rules that must be fulfilled to get certification and to be allowed to put a vehicle in circulation. Then there are all the new car assessment programs, or NCAP, such as US NCAP, Asian NCAP, and so on. They encourage car manufacturers to develop safer cars. These programs evaluate cars with respect to safety, and they deliver ratings with number of stars. In addition, several associations are performing their own evaluations, such as the assessment by ADAC of safety of baby and child seat, or assessment of the repair cost after low-speed crash for insurances. Finally, several manufacturers have their own internal requirements to differentiate them from their competitors regarding safety. Why doing crash simulations and not only tests? Often, at the beginning of a project, only CAD are available. Crash tests are destructive and hence are quite expensive, specifically on prototypes. If you look at this animation, one would need at least 2 or 3 vehicles to validate the car with respect to the displayed cases. Whereas with simulations, it is quite easy to evaluate different configurations and several variants. Finally, more and more certification by analysis are accepted by authorities. Simulations are giving to the engineers a better understanding of the behavior of any part of the vehicle or assemblies they are working on. Even if these parts are hidden during the crash, one can access stress state, plastic deformation, forces going through whatever component, absorb energies, etc. And so, simulations are helping to reduce time development. In the end, they enable to perform optimization analysis, in particular to reduce weight and cost, and robustness analysis to check the behavior of a design according to given dispersions due to manufacturing or test conditions or whatever. Let me now present you 2 slides that illustrate well the challenges of crash simulations for OEMs and manufacturers. These slides have been originally presented by Laurent Di Valentin, KI expert leader at Stellantis, at one of our conferences in 2018. First, the evolution of crash simulations at PSA, now part of Stellantis, over the past 30 years. Starting from models with simple structure and few elements used mainly for feasibility assessment, at the beginning of year 2000, every project was already gathering several KI engineers performing crash simulations. Today, current models may include several detailed dummies and may reach several millions of elements. These models tend to replace physical tests. The second slide shows the number of configurations with respect to different regulations and safety programs. Lots of frontal crash configuration, lots of side crash configurations to be evaluated if one wants to be present in the different regions. And this with less and less possible tests. It highlights the increasing importance of crash simulations at manufacturers. Now we saw the interest of crash simulations, let's have a look to what they are and to the approaches they use. We have to solve a physical problem in space and time while observing following physical laws: mass conservation, energy conservation, and momentum conservation. Today this physical problem is still modeled using finite elements for the discretization in space. Several formulations are available for the meshing: Lagrangian formulation, the elements deform with material; Eulerian formulation, the grid is fixed and material goes through the elements; and ALE formulation, in which the grid can move. Eulerian and ALE formulations are suitable for CFD applications. For crash applications, one will use Lagrangian formulation mainly. For time discretization, small increments are used, the time steps. To solve that type of problems, there are two kinds of methods, implicit methods and explicit methods. Implicit methods, the state of a given system is solved for several time steps at once. Explicit methods, the state of a given system at a given time is computed from the state of the system at an earlier time. Implicit methods are well adapted to static or quasi-static problems that are linear or not too much non-linear. In that cases, high time steps can be used and CPU cost remains small. Crash problems are dynamic ones with high deformations and contacts to manage, in addition to plasticity and often damage and rupture, so highly nonlinear, and that is why we are using explicit methods to solve them. The counterpart is that explicit methods are conditionally stable. An explicit solution is stable if the time step used for computation remains smaller than the critical time step. This critical time step can be seen at the time required for a shock wave to propagate across the smallest distance in an element. The solution is unstable if information passes across more than one element per time step. So, stability depends on two factors: the size of the smallest element of the model, this is a numerical factor, and the sound propagation speed in the model, this is a physical factor. Here is the classic flowchart used by explicit methods. Let's consider the state of the system is not at a given time. A new time step is computed, then external forces are determined, and through a loop over elements, strains and stresses can be computed, and with them, internal forces and contact forces. Accelerations can be updated. Finally, using central difference scheme, velocities and new nodes coordinates are calculated. And then we can go for the next cycle. Let me now introduce to you Alter Radius. Radius is a structural analysis solution using explicit method and developed to solve highly nonlinear problems under dynamic loadings. It is highly differentiated for its scalability, quality and robustness. Radius embeds features for multiphysics simulations and advanced materials such as composite materials. It has been used across all industry for more than 30 years now. Here is a brief overview of Radius standard applications. The main domain of applications of Radius is automotive, in which it is used at every level from component 1 to full vehicle, involving ruptures, honeycomb barrier models, dummies and airbags. It is used for the same type of applications in aeronautics, plane crash, occupant safety with dummies, but also for bird strike or debris or hail impacts. Radius is more and more used for drop tests of different kinds of goods, smartphones, bottles, helmets, and so on. Other applications of Radius are the ones based on fluid structure interactions, such as ditching in aeronautics, slushing of tanks, blast or bullet effects for defense industry. Finally, Radius can be used to simulate manufacturing processes, metal stamping, composite forming, or additive manufacturing. We can start now to consider our application case, the simulation of a crash box for Formula Student. We are going to see how to set up that kind of models, and then we are going to run the simulation and see a first analysis of the results. The aim will be to simulate the impact of a 300 kg rigid mass at 7 meters per second on a honeycomb crash box, check the deceleration and the deformation of the anti-intrusion plate. We are going to use the following data taken from a bachelor work of the Institut für Technische Mechanik at Stuttgart University, geometries of the crash box, of the anti-intrusion plate and of the bulkhead, metal reference for the plate, and honeycomb data for the crash box. The bulkhead will be considered rigid. Unit system for inputs and result is kilogram, millimeter, millisecond, GPa, kilonewton, and joule. In the end, what does interest the product manager is to have results a report that proves the product is fulfilling given requirements. And what the product manager can provide is the definition of the product. That is to say, its geometry, how it is assembled, and what are the materials. Now the big question is, how am I going from CAD to results and reports? For finite element analysis, the standard process is the following. First, get the geometries as clean as possible, get connection information and bill of materials. Then, one may proceed to meshing. First, selecting the type of elements to be used for the different components, spring, beams, shell, hexa or tetra, and then discretizing the geometries in finite elements. The quality of the meshing highly influences the quality of the result. Once the meshing is done, the setup of the model can start. In this step, one defines properties, assign materials, set contacts, loads, and boundary conditions. I'm going to detail this just after. At the end of this step, it is recommended to check the model. The model is ready and can now be computed by the solver. If the run ends normally, output files with expected results are generated. One can proceed to checks of the simulation and analysis of the results, and in the end, write the report. Let's focus now on the model setup. We got the geometries, the bill of materials, and the connection locations. We defined the meshing class and got the components of our model mesh. We now have to define properties of the elements, their formulation and their thickness for shell elements, or their sections for truss and beam elements. For material laws, they may already exist in a database we can access. If not, we have to define them. First, selecting the appropriate type of material law according to the type of behavior it is and to the data we have. And then, determining the corresponding parameters to fit the data. The data may come from test results or be found in literature, but keep in mind that for crash analysis, one cannot be satisfied with the elastic characteristic of a material, and its post-heal behavior must be characterized or estimated. That is to say, one needs to look for plasticity and even straight line dependency and rupture. We may now proceed to the next two steps, for which there is no specific order. For connections between the different components, there are different finite element representations that can be used. For example, for a spot weld, one can directly tie a node to an element, or use a rigid link between two nodes, or use a spring in between, or a cohesive element. The choice of representations depends on expected accuracy level and on the knowledge one has of the connection. The purpose of defining contacts is to prevent components from passing through each other or through themselves. We may define a global contact with all components of our models in. However, we may not need, for instance, to define contact between the very front part of a vehicle and its very rear part. Then we can create the load cases, set boundary conditions, loads, initial or imposed velocities, and so on, possibly merge impactors or dummies. Now we must think to output definition. What results do we need? How are we going to measure them? Are there specific nodes for which displacement should be monitored or connections for which forces should be controlled? We are almost ready to run our model. Before that, at the end of the setup, one should ask herself or himself, did I go through all the steps? And one should proceed to basic checks using a model checker or his own checks. Checks after the run are important too, before starting the analysis of the results. Now we've reviewed all the different steps. Let's start the setup of our model. For this application case, we are going to consider that the machine is ready. So I'm loading it in HyperWorks. We can have a quick look at the model. Check the components already defined, the crash box, the anti-intrusion plate, the bulkhead, and the impactor plate. For all the components, you can see that properties and material are not yet assigned. Before we start the definition of the properties, let me show you one radius card, the begin card, in which the unit system is defined. We are now going to create the different properties. Let's start with a simple one that we are going to use for the bulkhead and the impactor. We are going to consider these components rigid, hence we can use the default formulation, and only the thickness has to be defined. Here we may consider a thickness of 1 mm. I'm creating now a second shell property. This one is for the intrusion plate, which has a thickness of 4 mm. This one is deformable, and I need to define a bit more the formulation. First, the number of integration points through thickness. And I'm going to use an under-integrated formulation in the plane, which is standard in crash analysis, but that may lead to hourglass deformation. That is why I'm selecting a formulation with the physical control of the hourglass, the QEPH1. I'm selecting large deformation formulation with high small strain parameter and variable thickness with high thick parameter, and finally the method for calculating post-yield strain or plasticity with iPlast. We need a third property for the honeycomb. Since honeycomb is solid and orthotropic, I'm going to select a solid orthotropic property. For this one as well, I'm going to use an under-integrated formulation with physical control of the hourglass. In case of solid, this is HEPH formulation. And I'm defining a vector for the orientation of the material with V vector. I'm going to assign now the different properties to the different components. Let's start with the bulkhead and the impactor plate. Then the anti-intrusion plate, and finally the crash box. We are going to do the same for the material laws. I'm first creating a basic elastic material law for the bulkhead and the impactor. We may use steel characteristic for this one. As we use unit system based on kilogram, millimeter, and millisecond, stress entities are in GPa. For the aluminium of the anti-intrusion plate, let's assume we only got standard characteristic from a material supplier. For such material with elastoplastic behavior and with limited input data, we can use the Johnson-Cook analytical model with simplified input. The simplified input is accessible using iflag equal 1. And now I can fill the different parameters. Epsilon UTS corresponds to the strain at ultimate tensile stress. It is a bit different from strain at failure, so we need to do an educated guess. And here I assume that epsilon UTS is 70% of strain at failure, that is to say 90.6%. For the crash box, I'm going to select material law 28, which is one of the possible material laws for honeycomb. There are one Young moduli and one shear moduli per direction. And in this case, we are going to use curves that describe the yield stress as a function of strain in the different directions. I am first assigning the different moduli. To assign the different curves, I need to first import them in the model. For complex curve, I can import them through the plots ribbon. I can select the one I'm interested in, let's say the one for the direction 1. And now I have a curve that I can edit and rename. Like that. For more simple curve, I can also create them like that, let's say for the other direction. And here directly copy-paste the data from an Excel sheet. I'm doing the same now for shear direction 1, 2. And for shear directions 2, 3 and 3, 1. I have now imported all my functions. I can now go back to my honeycomb material law to assign the different functions. First, I'm going to adjust the type of function I'm using. Here, yield stress as a function of epsilon, or deformation. It will be the same for the shear function. I'm picking now for the first direction the first function, and so on with the other directions with the other function. Now I'm going to assign my material laws to the different components. So honeycomb for the crash box, aluminium for the anti-intrusion plate, and elastic steel for the impactor plate and the bulkhead. At the end, we can check that each part is defined with the right material law. We can now proceed to the definition of the connections and rigid. In our case, we are going to define rigids only. In HyperWorks, rigids are considered as elements. For the good organization of the model, I created dedicated components. I can now create the different rigids. I want the master nodes of these rigid bodies be automatically calculated by HyperWorks. The master node is a node that controls a rigid. Let's start with the one for the impactor plate. And now for the bulkhead, I can select node from the bulkhead. And select additional nodes from the anti-intrusion plate to model bolt connections. The rigid regarding the impactor needs to be updated. For this, I'm opening the solver browser. Here I can access the two rigids. Let's modify the impactor 1. I'm updating the mass of the rigid that will correspond to the global mass of the impactor. I would like now to tie the crash box to the anti-intrusion plate. For this, I'm creating a tied interface or interface type 2. I may adjust the formulation of this interface. In our case, I could have used the default one. Then I need to select the nodes to be tied. For this, I'm creating a set of nodes. I'm selecting the nodes of the rear face of the crash box. I'm selecting the elements to which those nodes must be tied. For this, I'm creating a surface. Here I'm selecting directly the component. And I am reviewing the definition of the interface. The interface looks good. We are now going to define the different contacts we need in this model. First, the contact between bulkhead and anti-intrusion plate. For this one, we can use a simple node-to-surface contact with interface type 7. I'm first creating a set of nodes with the node of the anti-intrusion plate. And I'm creating a surface with the bulkhead. There are several parameters that need to be set to properly define the interface. ISTF to adjust the stiffness of the interface, IGAP and GAPMIN to adjust the gap of the interface, that is to say the non-penetration zone on each side of the master surface. Here I'm using a variable gap. The gap will be automatically computed according to the thickness of the different components. Friction and I-form for the friction formulation, and INACT to manage possible initial penetrations. Let's do a quick review of this interface before creating a second interface to manage the contact between impactor and crash box. For this one, I'm going to use interface type 19. Interface type 19 is a combination of two symmetrized nodes-to-surface interfaces with an edge-to-edge one. For this one, I have to create two surfaces. For the crash box, that is a solid, I'm going to consider the external surface only. And a second surface for the impactor. For this interface, I'm using globally the same settings, except for the gap, for which I'm choosing here a constant gap. We can take the next step and start to define the load case. I'm first creating a boundary condition to fix the bulkhead. For this, I'm blocking all the degrees of freedom. And I'm applying this constraint to the master node of the rigid controlling the bulkhead. I'm then creating a second boundary condition to limit the impactor's displacement. This time I'm letting free the translation along x-axis, and I'm blocking all the other degrees of freedom. I'm applying this constraint to the master node of the rigid controlling the impactor. I have now to define the velocity that will be initially applied to the impactor. So I'm creating an initial velocity. I'm setting the components of this velocity, here 7 mm per millisecond along x-axis. And I'm going to apply it to a set of nodes will all the nodes of the impactor and the master node of the corresponding rigid on which I set the mass. That is why I'm creating this new set of nodes as a combination of two existing ones. We can finish this step by setting the duration time of this load case, and that corresponds to the final time of the analysis. Here we can consider that 55 milliseconds should be long enough, and if needed, it will still be possible to extend the simulation without rerunning the model from time zero. Now our load case is fully defined, let's take care of what we need to check the status of the requirements and if they are fulfilled. What results should be output from this simulation. A first useful information would be the force versus time in the crash box. And for this I can create a section. For this section I'm specifying its location and its normal direction. Creating the section, I automatically created a second entity, a time history output. Time history keywords are used to define output for plotting data, usually of a limited number of entities, such as forces, displacement, and so on. I'm going to create time history output for contact interfaces to be able to check contact forces. Time history for rigid body will give access to force and moments in them. Remember here that in HyperWorks, rigid bodies are considered as elements. I'm creating a time history for nodes so as to track the motion of the impactor and of the front face of the crash box. A time history for parts will output the energies in the selected parts, internal energy, kinetic energy, hourglass energy. Finally, I would like to measure the deceleration of the impactor. For this, I'm adding an accelerometer on the master node that controls it. And I'm creating the corresponding TH output. Before going forward, sorry, I just realized I forgot to define which variables I want to output for all these TH. If we look at the one at the section, for example, we can see that one variable group is defined, the def1 for default variables. I did not define these variables for the other time history. That is why I'm now opening the output blocks browser to quickly update those TH with the default variable groups. Dev groups include forces and moments for section, interfaces, or rigid outputs. For all these TH outputs, I still need to define the time frequency. How many time points do I want to have for all of them? Usually, we recommend to have about 1000 points. Here, if I set time frequency to 0.1, I will have 550 points and get enough information to plot curves. If we want to see animations of the crash, the deformation of the crash box and of the anti-intrusion plate, we need to add another type of outputs. These outputs can be generated as animation files or as H3D file. I'm first setting the output frequency time. With the frequency time equal to 1 millisecond, I will have 55 states plus the initial one. I can adjust the compression level of the H3D file that is going to be generated. And I'm adding contour outputs at nodes such as mass, mass change, contact force or pressure. contour outputs for shells and solids, like plastic strain or stress and strain tensors. Before exporting our model and running it, we are going to proceed to a couple of checks. First, I'm checking the mass of the model, the one due to the material densities and component thicknesses, that is structural mass, and the non-structural one, here the one I added on the impactor. Then I'm checking the possible intersection or penetration in the contact I defined. We can see that initial penetrations are detected in the contact defined between the bulkhead and the anti-intrusion plate. Actually, they were expected. Remember, I used the variable gap for this contact. Anti-intrusion plate thickness is 4 mm, bulkhead thickness is 1 mm, so the two parts should be distant from 2.5 mm, and they are only distant from 2 mm. Hence the 0.5 mm detected penetrations for all the nodes of the plate. As I define inacti equal to 6 in this interface, I'm not going to correct these penetrations, but it would be here really simple. One would just have to move the bulkhead back by 0.5 mm. Finally, I'm running HyperWorks Model Checker to look for possible setup mistakes. Here, it's only reporting a warning due to a parameter definition in an interface. Except this warning, no error has been detected, so I can be confident and launch my simulation. There is the very last thing I'm going to add before exporting the input deck, a control for the time step. I'm going to define a constant nodal time step to avoid the time step from dropping below a given limit and the simulation stop progressing. As a counterpart, mass may be added to nodes if needed. I'm setting it to 0.001, 0.9 is a safety scale factor. Nodal time steps are evaluated during the first stage of the simulation, the starter. So usually, this time step control is defined after having run a first starter of the model. I'm exporting now the radius deck, setting the name of the input deck. The deck is usually divided into two parts that correspond to the different stages of the simulation. I'm going to detail them just after. I'm checking that the engine file for the second part of the simulation will be generated as well. In the Alter Compute console, I'm loading the input deck file. As you can see, there are two files. I'm selecting the 0.rad one and I'm launching the run. We can see that several information regarding the progress of the simulation are displayed. While the simulation is running, let me detail you its different stages and the different files. As I said, radio simulation can be divided into two parts, the starter and the engine. To the starter corresponds one input file, the 0.rad, that contains the model definition. During this step, Radius is checking the model setup and compile it in restart file 0.rst. RST files are binary files and cannot be edited. It is also writing an information file of what it is reading, the 0.out file. This one can be edited and it is important to check the information it contains. The second part of the simulation is the engine. There can be several engine steps. Each one of these steps is controlled by an engine input file, 1.rad, 2.rad, and so on. Note that the first engine file can optionally be merged to the starter file. During this stage, Radius is performing the computation of the numerical problem from time 0 to the final time defined for the simulation. It is creating RST file 2 that will be part of the inputs of the possible next step. It is also writing an information file of what it is reading and of the progress of the simulation, the 1.out file. It can be edited too, and it is important to check the information it contains. And of course, it is generating the result file we define in the output step of the setup. Animation files such as H3D1 and time history file T01 for first engine, T02 if there's a second engine, and so on. Let's go back to our simulation. The run is ending with normal termination. I'm now editing the .out files. Note that 0.out file could have been edited and checked before launching the engine part of the simulation. In these files, I'm first retrieving the radius version used for the computation, then the list of the different entities of the model, followed by detailed settings for different entities, such as in the zero.out file, the material law we set for the aluminium. Here we can see the data we specified, and the computed Johnson-Cook parameters are exposed here. We can jump to the end of the file to find a summary of the detected error and warning. Here there is no error, and there is only one warning regarding the initial penetration. And if we look for details of this warning, we can see that these initial penetrations correspond to the one we found with HyperWorks penetration tool. I'm checking then the total mass of the model. I can also find the coordinates of the center of gravity and the inertia of the model. The minimum time steps assessed at time 0 can be found for each type of elements in the model and at nodes 2. A chart of the distribution of nodal time step is available, with an estimation of the possible mass change according to different settings of constant time step control. Finally, a summary of incompatible kinematic conditions is given. In our case, there is no incompatible kinematic condition. Let's have a look now to the one.out file. First, one can retrieve the number of domains and processors used for the computation. And below, what has been read from the one.rad file, here, the runtime, for example. The main part of the engine file is the list of the printed states of the computation. The frequency output of this printout can be adjusted. And for each printout, the following entities are reported. First, cycle number, current time step, and current entity controlling the time step. Then the energy error, the internal energy, kinetic energy, and external work. And at the end, the mass error. Here, final energy error and mass error are really small, less than 1%. At the end of the engine.out file, CPU time information are given. Here we can see that the elapsed time for this simulation, the time seen by the user, is approximately 200 seconds or a little bit more than 3 minutes. Our next step is a physical validation of our simulation. For this, I'm loading the H3D file to see the animation of the crash and check if boundary conditions, motions, contacts, and deformations are correct. And we can see that they correspond to what is expected. So I'm going now to load a template file with a pre-recorded post-processing session. It is based on animation NTH files and can be used again for future iterations. I'm selecting Happen Mode to create new pages after the existing session. First, we are going to check energy balance. Kinetic energy starts at the expected value. Total energy remains constant. There is limited contact energy. Mass variation, mass changes are really small. And time step variation that correspond to what we specified. Then we can have a look to the max displacement of the anti-intrusion plate, approximately 10 mm, to the stress in the crash box, and to the plastic strain in the plate. On the next page, forces monitored in different entities are plotted. Force in the contact between impactor and crash box, reaction force in the fixed rigid body, force in the crash box section. All these forces are consistent. And on the last page, we can view deceleration of the impactor, displacement of points on the front and rear face of the crash box. We retrieve the 10 mm intrusion. From this, we can compute the crash box residual length from 200 mm to 60 mm. And finally, absorb energy from the crash box and from the anti-intrusion plate. I'm going now to show you how to export these results in a presentation. I'm quickly defining the structure of the report. I'm first adding 2 slides with videos of the different animations of my session. Then I'm adding captures of all the other pages. I'm running the report to generate the different entities. And then I can export it. And we have our report with the different results. This ends this webinar. I hope you enjoy it. Thank you for your attention and have a nice day.
Thank you, Pierre-Christophe, for your presentation. Thank you, everybody, for attending the session. We are at 12:30 now, European time. But I hope we can take a moment for some question and answers. Especially, we have one question for you, Pierre-Christophe, is I think something you explained during your presentation, but maybe you can explain more about different kinds of formulation. I mean, Lagrangian formulation, Eulerian formulation, and ALE, Lagrangian Eulerian arbitrary. So would you please come back on these points to mention which formulation can be used for which kind of application, and if there is a, for instance, for the case, a special case of crash, which formulation you mostly use? Thank you.
Hello, Hossein. Yes. As I said, for crash application, Lagrangian Lagrangian formulation is yes, the standard formulation to be used, the standard modelization to be used. And it is the case for most of the structural analysis, every impact of structure or drop test and so on. ALE and Eulerian formulation, as I show also in the fluid and structure and interaction application, will be more adapted for fluid modeling, of course, such as the fluid in a tank, or yes, whatever other fluid, but it can be also the air, for example. And it is the case when we are working on blast application, for example, so to model all the detonation, whether the mine is put in the sand or directly in the air. All this part of the model will be will be done with Eulerian or ALE formulation. But the structure, for example, if we think back to the example with the vehicle above the mean, the structure of the vehicle will be defined with Lagrangian formulation. And we are going to define a fluid structure interface in between, so as to manage the effect of the blast or of the fluid, here the air and the sand, for example, on the structure. Other special cases may be bird strike, for example, or hail impact. In that case, we are using SPH. So this is kind of Lagrangian still formulation, but with particles, hydrodynamics particles. This is also possible in radios. And I guess this is mainly the main kind of application I'm thinking now. I don't know if it answers your question, Hossein.
Yes, thank you very much. I would like just to mention for those who want to learn more about radios that we have a lot of materials, e-learning materials are available on Alter University website. Please go through that, and also we have an ebook available. We are in the advanced session, so we have a lot of advanced questions as well, and but some of them are related to the usage of the software. and I'm not sure that we can, answer to them right now, because we need to interact with the users to understand if something is wrong or not. So I invite all questions, or all people asking questions about the usage of software to refer to support forum available in alteruniversity.com to ask questions, to get answer to their questions. We have also some other questions, especially to the use of some material laws, and one, or for instance, one question about is the following: if I want to simulate a particle tracking in friction stir welding, can I use material law 4 with SPH for tracking particle distribution? So it's of course it's a very sharp question related to one topic, but just question, Pierre-Christophe, do you think that SPH method can be applied in this case for stir welding and friction?
Yes, I guess we can try to use that kind of approach, but this is a complex simulation here to have the thermal effects also due to the friction, and this is possible through the contact interface in radios to generate heat through friction. HPH, I guess, is maybe the best approach to have the mix of the different material expected during the welding. But HPH has a cost too, so the zone or the melting zone or the welding zone has to be limited, and we can try to use also solid to SPH approach, for example, to limit the computation time there.
Okay, thank you. There is also one question about the usage of the old version of HyperWorks. We recommend everybody to download and use the last version. If you use an old version, so
I guess there are two questions here. Yes, of course, every old input deck of radios, whatever the version, maybe not very, very old ones, but 2017 or even 2014, yes, you can run them with the very last version of radios. There's no issue with that. Radios is supporting its previous input deck format. There's no limitation on that, unless we are really looking at really old, I don't remember, but maybe version before version 5 of radios, for example.
Okay.
And then, of course, for the setup of radios model, I'm of course recommending to use the latest version of HyperWorks with all the functions and options I show in the presentation and in the demonstration. Yes, most of this setup will be a bit more complex with old version of HyperMesh, for sure.
Okay, thank you, Christophe. Maybe the last question, it is about what does it mean, error in input consistency in radios? So I'm not sure that this question is clear, but
yes,
when you have, maybe the question is about error and warning or something like this. I don't know.
Maybe it's something that's user faced.
In general, for instance, between warning, error, something in general, because if it is very usage case, I recommend to go to the forum support to get answer.
Yes, warning in the warning in HyperWorks, and the errors reported by HyperWorks might be different the errors reported from radios. If there is an error during radio starter, you will not be able to run the engine file afterwards. So these errors are mandatory and need to be corrected. It is mandatory to correct them, sorry. The error reported in HyperWorks may be methodology errors. So it depends on the methodology that have been captured in HyperWorks. So some users want to have some error reported if they are not using the correct number of integration points in properties, for example, for shell. Warning, it really depends, and one need to look at warning in the starter file, as I did in the presentation. We need to check if these warnings are relevant or if they are already managed by some option in the solver already, such as the management of the initial penetration in the contacts. That is possible. Yeah, that's mainly the different message we can have either from HyperWorks or from Radius at starter.
Okay. Thank you very much, Christopher, for the question. Thank you all for your participation to this webinar, to this session. I think we had a great presentation, and thank you everybody to attend. I hope you can attend other sessions of student webinar. We continue to host them in the coming days. So looking forward to see you again here. So I think we are at the end of this session, and we can close the session now. Okay. Thank you, everybody. Thank you for your attention during the presentation, and have a nice day. Bye-bye.